Hello again, everyone. Welcome back to our next lesson. Uh, this lesson begins on page 24. We're going to continue using the delta process to find the derivative or the slope function of any other function so that we can calculate the slope of a tangent line of a curve at any point. Now, you will recall that we left off in the last video right here. We had actually found the derivative or the slope function of f of x equals x squared. That was the original function. And here's, again, this is the technique we use. It's called the delta process, or it's also called the definition of the derivative. So if you see a question that says that, that means they're expecting you to use the delta process. We used the delta process. It was a fairly complicated, or not really complicated, but it was a drawn out calculation. And we ended up with there was the slope function. You see that? The slope function was actually equal to 2x for the function f of x equals x squared. So here now on page 24, this continues with the lesson on the delta process. Again, here's the function f of x equals x squared, and they've actually drawn the graph for us again. Now remember, what we did previously was we calculated the slope of the tangent line at the point x equals 1, and the tangent line looked something like that right there. All right, so anyway, here's what the slope was. The slope at any point is equal to 2x. That's the slope function. Now we can use that slope function, remember, not just at x equals 1 like we did. We can use that anywhere on that curve. So for example, if you look right here, this is a function that gives us the slope of the tangent line at any x. So if x is equal to 0, for example, well, let's look at the tangent line. There's 0 right there. And the tangent line you can see is a horizontal line this time, isn't it? So at x equals 0, the slope would equal 2 times 0. You just plug the x value in. And so that slope is 0. And sure enough, it is. I mean, because it's a horizontal line. At x equals 1, now we've already done that. That's actually the calculation we did previously. So the slope would equal 2 times 1, and that's equal to 2. And sure enough, that slope right there is 2. It's exactly 2. At x equals negative 1, well, now we can't quite see it, but it would be about right here. The curve would look kind of like that right there. You see, it would be a negative slope, wouldn't it? Well, if you plug in negative 1 into the slope function, then it's actually equal to 2 times negative 1, which is negative 2. And sure enough, it looks like it's negative 2. It really does look like the slope of the tangent line at that x value would be negative 2. So what we've done is we've actually calculated a different function. It's called a slope function or a derivative that will allow us to calculate the slope of y equals x squared or f of x equals x squared anywhere, anywhere on that curve. And that's one of the powerful things about it. Here is your definition of what we mean by a derivative. The derivative of a function is expressed as a function is, and there. Now that's the result of the delta process. You see the limit as h goes to 0 of f of x plus h minus f of x all over h. Now that formula, that's provided on a formula sheet for you. You don't need to memorize that, but you do need to know when to use it and how it's used. Now, the funny thing is, look what they've got put in front of that. There is a symbol for the derivative or the slope function. That's a symbol, and it reads the derivative of f with respect to x. That's one way you can say it. A more common way of saying it, most people say it this way. Look at that. F prime of x. F prime of x is the derivative of f of x. There's other ways that you can write the derivative, other notations. Here's some of the more common ones right here. This right here, this symbol, you see that little prime symbol right there? Well, this is just read y prime. That's the way you would pronounce that. But it means the same thing as f prime of x. In fact, here's f prime of x right there. Look, that's the third one in the list. Here is another one. You don't see this one very often, but again, it is a symbol for derivative. It stands for the derivative of y with respect to x. Here's another symbol that stands for derivative, dy by dx. So if you see that, remember, it means the same thing as f prime of x, just different ways that there are different symbols, different notations. They all stand for the same thing, the derivative of a function. Okay? And the process of finding a derivative is called differentiation. All right? And that's where differential calculus gets its name. A whole branch of calculus based on finding the derivative of functions and the applications of that. So remember, here's this. Look at this blue box on the bottom of page 24. All right, I'd highlight that if I were you. Remember that at a point x comma y on a curve, the slope of the curve is the same thing as the slope of the tangent line at that point on the curve, and that, by golly, is equal to the derivative. Okay? And we can get the derivative, or we can get the slope of the tangent line, whatever, by using the delta process. Well, for now anyway, we'll use the delta process. So on page 25, they've just got some other examples there of how to use the delta process to find the derivative of a function. Note carefully, please, the way this problem is worded. It says, find the function for the slope. Well, by golly, that means the derivative. So they want you to get the derivative of the following functions using the definition of the derivative. So now what that means, of course, is using the delta process. My goodness, this marker is not very good, this stylus. All right, so what we're going to do here now, I'll do another example with you. I'll try B right there. Okay, we'll try that one. And then I'll leave the other ones for you to try with the delta process. And we'll do some of these in class as well. So make sure you watch these videos before you actually, before the class starts. All right, so let's do B right there. Okay, so the function is f of x equals 2x squared plus 3x. I want to get the derivative. All right, now remember, we can actually use the notation here now. I can say f prime of x, that's the notation for the derivative, is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. All right, so here's what we go. This is what we have to do. So this is equal to the limit as h goes to 0. Step number 1 would be to correctly put x plus h into the function first, and then subtract the original function. Now make sure you use brackets for that. Brackets are absolutely vital. Sometimes I like to use square brackets sometimes. Although you don't need square brackets, but you can. So let me see. I'm going to put x plus h into the function right here, wherever I see an x. So this is going to be my first result. 2 times x plus h squared. Now be careful with that. Remember, that's a binomial squared. And then 3 times x plus h. And I'll put a square bracket around that. Now remember what that is. That is f of x plus h. All I did was I took the function, and wherever I saw an x, I replaced it with x plus h. And then there's a minus. Now you're subtracting the original function, f of x. Please use brackets here. Remember I mentioned in the last video that the brackets are going to be important. They're going to matter because there's a minus in front. All right, now you see what's going to happen to that plus 3x? Excuse me. That plus 3x is going to become a minus over h. So after this, the rest is just being very, very careful with your calculations. All right. So we've got 2 in front of Now remember, x plus h, we squared that before. In fact, if I go back and look on the previous page, or a couple of pages back, there's your x plus h right there. Let me get my blue ink. There's x plus h squared. And remember what it turned into. It turned into x squared plus 2xh plus h squared. Well, anytime you have to square x plus h, you're always going to get that exact same result. All right, it's going to be the same thing every time. So even down here now, all right, when I do this calculation here, let me go back to the red ink. This is going to become 2 in front of x squared plus 2xh plus h squared, closing bracket, plus, now multiply through this set of brackets here by the 3. You can do that now. 3x plus 3h. And now remember that the minus in front of this second set of brackets here distributes through that through the brackets. So you're going to have minus 2x squared minus 3x. Now watch carefully. Remember now, you have to show these workings in a quiz or in a test, and I'll be looking at these signs and things to make sure that you're doing this all correctly. So now we'll multiply through this set of brackets by the 2. And by the way, if you see anything there that you can cancel now, if you see anything that vanishes, that disappears, well, why not cancel it out right now? So for example, let me get some blue ink again. Do you see plus 3x minus 3x on the top? Well, those two terms cancel already. You can wipe those out now. You can wipe those out now. No problem. So we have the limit as h goes to 0 of 2x squared. Now I'm multiplying through the brackets here now. Plus 4xh plus 2h squared. And then I also have plus 3h minus 2x squared all over h. Well, we've multiplied everything out. We've squared what we had to, and now let's just keep reducing, everyone. Let's keep seeing what will vanish, what will disappear, and hopefully this expression becomes easy enough that we can eventually, when you do use direct substitution, and when you do put in 0 for h, you won't end up with an undefined expression. Now, do you see anything else there that cancels at this step? Anything else? Oh, look at this. 2x squared minus 2x squared. They're gone. They disappear. So really what you're left with now is the limit as h goes to 0 of 4xh plus 2h squared plus 3h all over h. Now, what would you do here next? What would you do here now? Well, remember, you're still looking for places that you can simplify, cancel, using some kind of algebra. And I can see that the numerator now has a common factor of h. Now, even if there was another common factor, I wouldn't remove anything else, just the h, because it's only the h you want to cancel with the denominator, you see? So take out an h from the top. You're going to be left with 4x plus, and now 2h squared divided by h is 2h, and plus 3h, well, the h comes out of that, so there's just plus 3, or h. And now, here we go. There's the magic step, I like to call it sometimes. All right, they're gone. Oh, I'm running out of room. So now, what would my next step be? Well, I'm left with the limit as h goes to 0 of 4x plus 2h plus 3. Now, plug it in now. Use your direct substitution now. And in fact, there's only one place there to put your 0 for h, isn't there? So you're going to end up with 4x plus 2 times 0 plus 3. And we're Done. Look at that. Now again, notice you don't end up with another number. Usually you don't. Sometimes you do end up with just a number. If your original function is linear, then you'll just end up with a number. But for the majority of cases, you end up with another function. So that, everybody, that's your derivative. That is the derivative of the original function. So that, in fact, let me just come down here now, watch. F prime of x is equal to 4x plus 3. Now, by golly, you can use this derivative to find the slope of this function here, the function that you started with, at any point on that curve, anywhere at all, anywhere. You could use that derivative to find the slope. And you might not realize yet how important that is and what a powerful technique that gives you. But it is very, very powerful. Okay. Now the other ones, A, I'm going to leave for you to try. This example on the bottom of page 25, find the derivative of f of x equals. Now I'm going to make a suggestion here, everyone. Look at this function right there. They want you to find the derivative, but for now, don't try to take the derivative of it in that form. In fact, what you should do is simplify that first. All right, simplify. All right, now I'll probably look at this one in class. But you definitely should simplify that one first. It's much easier to simplify rather than taking the derivative of it in its present form. So what I mean by simplify, of course, is square out the x minus 2. Now again, remember that's 4 multiplications. Whatever you get when you square x minus 2, multiply that by negative 4, and you're going to have a trinomial, of course, when you square x minus 2, and then combine the plus 4 with that. You should end up with f of x equals just a simple trinomial. All right? So do that first, and then go ahead and use your delta process. Oh, by the way, look at this. Look at this. Remember I said that in some textbooks, instead of using h, they use delta x? Oh, delta x, and there's delta x, and there's delta x. When I was in university, that's practically the only symbol I saw was delta x. But it means the same thing as h. You can, if you wanted to, you could even replace the delta x with h, and you'd still get the same result. You still get the same answer. All right? So I'll get you to try those. And now on page 26, there's some more examples. Now, some of these might be a little trickier than I might ask on a test. All right? Like, I don't think I'd give a square root one on a test. That one is actually pretty tricky. Now, you can try it. You can try it, but that's probably a little more complicated than I would give on a test. All right? So I'll stop there, and that, ladies and gentlemen, is your derivative. Powerful, powerful stuff. Really, really useful as well. You wouldn't believe the problems that can now be solved hundreds of years ago. The problems the solutions that this opened up. All right, lots of problems that couldn't be solved before. Now they could. All right, so I'll stop there with this video. And you try those practice questions. Make sure you check your solutions. They're all posted on D2L. I'll go over this again in class with you. And have yourselves a great day. Bye-bye.